So thank you very much for the introduction. This is joint work with Nergiz, Yuca, Dustin, Kern, Nikolay, Matyunin, Stefan, Katzenbeisser, and Christoph, Krauß. And we already heard yesterday in the other EV charging session that EVs are getting more and more important, especially in Europe and Asia, because they're better for or more environmentally friendly than traditional combustion engine vehicles. And well, of course, instead of adding fuel, you have to charge them. And to pay for this, there are often app-based approaches. You have to install a custom app, or you can pay via credit card. But there's also the plug-and-charge mechanism in ISO 15118, which enables you to just plug in your vehicle to the charging station, and then the vehicle will authorize the charging session. And basically, there's nothing else you have to do, no credit card required for all the payment and billing if you're set up for this. However, the issue here is that privacy has not been considered within this standard. And one of the things here is the so-called e-mobility account identifier, the eMite, which is shared with all the involved parties. So which are these involved parties? Here you can see an overview of the plug-and-charge architecture. Of course, you have your electric vehicle, you have the charging station, but there's also a charging station operator that operates all of these charging stations. And there is the e-mobility service provider, which is the provider where the vehicle owner has the charging contract, which is used for the billing, of course. And there might also be a so-called contract clearinghouse in between these two parties, which mediates between the CSO and the EMSP in case they do not have a direct business relationship. But we will not really look at this in this work. So how does that work? Well, if you establish a charging contract, it will be installed on the vehicle, and it's authorized by the EMSP, of course. And then this is identified by this so-called eMite, the account identifier. And then during a charging session, this account is, or this contract is used to authenticate the session towards the charging station. That might also be online directly with the CSO, or there's also the option for an offline authentication, and it will be checked later. It uses usually a PKI and signed then with a certificate signed by the EMSP. Then the charging station operator, of course, has to record all the charging sessions and basically aggregate the consumption in a database. It can then bill the EMSP for all the energy consumed by vehicles that have a charging contract with the EMSP, and the EMSP can then bill the individual users. So while there is a lot of security consideration here, we've already heard yesterday about, for example, the security levels in the OCPP protocol, which is between the charging station and the charging station operator. There's also TLS between the EV and the charging station, for example. So that has been considered, but privacy has not. And to enable all this billing between the parties, the eMite is basically passed around through all these parties. And from a privacy perspective, now that, for example, the charging station operator knows the eMite, he also knows the location, of course, of the charging stations where the vehicle is charging, and thus he can link this data. And there we have a so-called honest but curious attacker, right? It will stick to the protocol that is defined, but it will try to derive additional information, and it can easily, in this case, derive, for example, movement profiles of vehicles because it knows all the different charging sessions from one vehicle at its own charging stations, and the CSO knows exactly when the vehicle was where. And that's the same for the EMSP because he also has access to to all these individual charging sessions. And that's what we want to prevent, basically, to ensure that there's privacy. We want to try to achieve unlinkability between these charging sessions, so you don't know that one session was, or like two sessions were originated by the same user or the same car. Of course, the system still has to be secure against malicious EVs that want to charge for free, for example, or charge on behalf, on the bill of another EV, of course. And also, there might be malicious charging stations that try to spoof basically charging by EV and maliciously charge users for consumptions or like charging they didn't do. Of course, there are already a few works in this area that define different EV privacy-preserving EV charging systems. In this work, we focused on real strong privacy guarantees. So we also consider privacy against the e-mobility service provider, and we didn't want any specific hardware requirements or like additional backend entities that are required. On the downside, this is more theoretical work. We don't have like a proof of concept evaluation as some other works do. So the idea we followed was we looked at oblivious random access machines. I'm not sure if you're familiar with the concept. It's basically designed for cloud computing, and the idea is if you just want to outsource your database to a cloud computer, but you don't want the operator of the cloud to learn anything about what you do there. Of course, you can just encrypt your data, but the operator will still learn a lot of metadata, like which files you access, right? Which records within the database. And that's basically what ORAM protects against. And what we needed for our work was a multi-client ORAM, so that we can have multiple clients, not just one that owns the complete database. And we found a framework or like a model from Maffei et al., which really fit our requirements. But we then found, or we had to look for an implementation actually that we could use. For example, we didn't want to have anything that required communication between the clients, right? So that vehicles have to communicate for one charging sessions. That would be worse. So one thing we found here is the implementation from Chow et al., which is based on full homomorphic encryption. And the multi-client ORAM model basically looks at like this. You have a database owner, which will initially transfer the database to a server, and then you have multiple clients which get access to specific records in the database and can then read and write these records, and they only can access the records they specifically are given access to. So our idea is that we put this ORAM database at the CSO, and so basically each charging or like each vehicle has one entry in this database where the consumption is stored, and the CSO cannot learn which entry was updated by the vehicle to ensure the privacy here. So for the setup, the EMSP generates the database and all the keys required, sends the database to the CSO, and then an EV can register with the EMSP as usual, and basically during this registration it will get assigned one entry within this database and also the keys to access this entry. And then for charge authorization, the EV can basically send an update to the database where the aggregated consumption of the EV is stored within this entry. However, what is not considered in the ORAM model, their clients are supposed to have full access to the entries they have, and here now we want to ensure that the EV actually updates the entry with the correct consumption, right? So we introduced the non-interactive zero-knowledge proof to ensure this without revealing the identity of the vehicle. And then for billing, the CSO can just pass the database back to the EMSP, which is able to decrypt the database and then knows the aggregated consumptions over the complete billing period, like not the individual sessions, but just the aggregated amount to be able to bill the vehicles. So I will just show you a bit of the crypto in the paper so that you get a feeling. Maybe don't try to understand all of it now because it will probably take a bit of time, right? So we have the setup algorithm here, master key generation. We have the initialization of the database and establishment of the proof keys as well for the NISIC proofs. During registration, the EMSP basically assigns an address, which is a database entry to the vehicle, and also provides it with the required keys to access this entry. And then during the actual charging session, we have some initial authentication not shown here. Then we know basically at the end of the session the consumption by the vehicle. There's some key derivation here as well. But then the vehicle computes an update based on the ORAM system. Basically, it's a fully homomorphic encryption of the consumption and also of a signature over this consumption. And we also compute a non-interactive zero-knowledge proof I've talked about before. So within this proof, we show that the encrypted value within the update is actually the consumption measured as measured by the charging station, and that the signature will verify for one of the keys, basically for at least one entry within the ORAM database. And the idea actually for the fully homomorphic encryption here is that the CSO goes over the complete database with this add algorithm and basically computes for every within. I'm not sure who is familiar with fully homomorphic encryption. Basically, it's encryption where you can do any computation within the encryption, right? And you don't know if the computation was successful or not. So if we do verify the signature here and only for the address where the car is allowed or got access to, the consumption will be updated with the correct amount, and that one update will be performed. In this case, it can only be one. We showed before with the zero-knowledge proof. So with this, we addressed the security and privacy issues we wanted to address. For a malicious EV, we have the NISIC proof that shows that the update will work and also will contain the correct assumption. We also have the security of the ORAM scheme that protects against, for example, a charging station trying to update the wrong record. We have the strong privacy property of the ORAM scheme so that the charging station operator does not learn which record was updated within the system, and so it cannot learn the identity of the vehicle and is not able to link those individual charging sessions. And also for the EMSP, it only learns the aggregated consumption and not each session. There are some limitations. We assume, of course, the existing security like TLS between the CS and the EV. You talked about it only considers honest but curious EMSP and CSO, which are also not colluding. So you could basically send the database after each charging session to circumvent this. Of course, you cannot protect against the compromised CS for enabling free charging. We have kind of this limitation that the consumption values or the energy costs should be fixed in advance for one billing period. Maybe there's also some way to get rid of this limitation, but that's at the moment. And also there might be other channels, for example, just a camera of the license plate to identify the vehicle that's not considered here. For performance, well, this FH full homomorphic encryption over the complete database, you can imagine that's very expensive. So that makes it more of a theoretical construction at the moment. It's not practical with the current FHE schemes as I'm aware of, at least. But there is a lot of improvement and in this space at the moment. So And maybe we also find some other ORAM implementation in the future that's more efficient. And NISTIC proofs might also take a long time, but well, charging sessions take a long time, and so that might be less of an issue. So in conclusion, we presented a novel approach for privacy in EV charging. It prevents the linking of different charging sessions, provides privacy against both the CSO and the EMSP, and it does not require additional backend entities or a TPM or other special hardware. The practicality still depends on ORAM. Yeah, and there's a lot more to do, but like a practical implementation. But with that, I'm looking forward to your questions.